Good morning. No, good morning. Okay. Thank you. All right. If you have any questions, just let me know in the chat before we start. It could be about anything. I don't know. Okay. All right. Okay. I don't see anything. All right. So let's start. So this is section 1.4 from the book. And many of you have seen this before, the concept of linear independence. But now we're going to talk about this in general vector space. And general field. So this is something you haven't seen, right? You've seen it for real numbers, but not when we take matrices or polynomials and so on. Hello, I'm struggling to understand the ninth axiom of a field. I don't remember what the 1 times. Yeah, let's talk about that in at the end. But yeah, I mean, like, yeah, okay, let's talk about that at the end. All right, so linear dependence. All it says is that you give me some set S with elements V1 to Vn. And it says that you can find some non-zero coefficients so that when you add them together, you get 0. So I think I write it below. So in other words, what can you do? Suppose that the first coefficient is not 0. It could be aj, but just for simplicity, suppose the first one is not 0. Then what can you do? So you move them to the other side. So ak vk for k starting from 2 to n. And then you know that f has multiplicative inverse. Okay, multiplicative inverse. So you multiply by a1 inverse. Okay, so then this becomes the identity 1f. And then here you just write it as summation of a1 inverse ak vk. So v1 is just this okay. So that means you wrote v1 in terms of the other ones. So that's why it's called dependence. So v1 depends on v2 to vn. Okay. So that's what dependence means. And linear independence is when you cannot do that, is when given this formula, you are forced to have all of them to be 0. okay? They're all forced to be 0 when when one of them is how does this work? Okay. Yeah, so it forces all of them to be 0. And if that's the case, then it's called linearly independent set. So let's start with a simple example. Take these 3 vectors. So pictorially, it's the 1, 0. What else? 1, 1, and then 1, 2. So it's somewhere over here. So these 3 vectors are dependent. So let's see why. Well, I didn't write it. I'll do it myself. Okay, so let's see what the dependence is. What's an easy one? Let me write the 1, 2. So 1, 2, you can split it as 1, 0 plus 0, 2, okay, by vector addition. And then I write it like this. I take out the 2, 0, 1. Okay, so now I have to create this 1, 1. So let me just add it and let me see. So I don't like this. Let me do it some other way. So I know what I'll do. So I will subtract and add. So I add 2, 0 and subtract 2, 0. That's easier. Okay, now we're in business. So this guy becomes minus 1, 0. And this guy becomes 2, 2. So I take out the minus 1. I have 1, 0. And I take out the 2 and I get 1, 1. Is that okay? Oh, yeah, good. Thank you. So yeah, exactly. Very good. I think you got the 1, 0 in the wrong direction. Let me see. No, I think it's fine. Yeah. Is it okay now, Rahul? The way I wrote it? Because these two subtract each other, right? So you get minus 1. Okay, I mean, you can let me know if you still disagree. So yeah, so 1, 2 is what we call redundant. Okay. Like 1, 0 is on the x-axis. Oh, yes, 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 yes. Ah, oops. Yeah, thank you. Yeah. By the way, please post it on everyone because these are good questions. It's fine. Okay, so yeah, this is 1, 0. Thank you. And this is 1, 1. And this is 1, 2. Yep. All right. Yeah, so 1, 2 is redundant. So S is linearly dependent. All right. Now let's do some more general stuff. So here we have 3 polynomials, okay? And we're going to show that these are linearly independent, even though they look dependent, right? So you have X here and you have another X here. They look very close, but in fact, they are independent. So let's see how you do this. So always you start with, I mean, for now, we're going to do this, but later on, we will do this with determinants. We will check Li with determinants because it's much faster. All right. What do? You write C1 times your first vector, C2 times your second vector, and C3, and you set them to 0. Okay. You regroup in terms of the standard basis. Okay. And from here, you use the following fact. You use that by the fundamental theorem of algebra. Fundamental theorem of algebra said that Pn of x being 0, it has n roots. So let me say that because this is too confusing. So every Pn of x for x in complex has at least has n roots, all right, with multiplicity. All right, so one implication of this is that Pn equaling x for all x implies that the coefficients of the polynomial are all 0. Okay, 0 coefficients. Because it cannot have more than n roots. Here it says that every x is a root, but it has at most, it has exactly n roots, but the point is it cannot have infinitely many roots. Okay, yeah, every coefficient is 0, exactly. All right. So yeah, exactly. So let's see what relations we get. So we use fundamental theorem of algebra and we get the following relations. We get C1 minus C2 is 0, the first one, second one, and third. So this is a system, and you solve that 3x3 system. But it's an easy system because you have C3 0, so you put it here. So then you get that these two are 0, but then they're equal. Okay, I think that's okay, right? I can do it in detail if you want. So that will indeed give you that all 3 of them are 0. So what happened was that asking for this forced the coefficients to be all 0. And that's exactly the definition of linear independence. Okay, that's all. Good. All right. Yeah, you can check for yourself whether this set is linearly independent or not. It takes some work, but we won't do it now, but you can do it on your own for practice. All right, now here's a more tricky example. Let me explain all the notations here. So P2 of F3. P2 of F3 are polynomials of the form A01 plus A1x. And we take AI and x to, and one more, A2x squared. We both take them to be in F3. This is the modulo group, 0, 1, 2, where we have modulo operations like, 2 plus 1 is 0, 2 times 2 is 3 plus 1, so it's 1, so modulo 3. And we can have a polynomial over that space, and we can have a polynomial space over that field. Okay, so I wanted to do this example so we practice a little bit. And yeah, the question is, take these polynomials, these two, and show that they're Li. So let's do this more tricky example. All right. Okay, so what does it mean to be Li? What condition do you check? So you take each of the vectors, a1x and 2x squared, and you set them to 0, and we want to show that a1 is equal to a2 is equal to 0. Okay, that will give us Li for this set S. All right, so how do you do it? Let me go on the left. All right, so a1x plus a2x squared is equal to 0 for all x in the field. That's the statement. Okay. All right. But there's only 3 elements. So that's easy. So let's do that. So for x equals 0, you get what? You get a1 0 plus a2 0 equal to 0. So there's no new information here. No new info in this case. What about x equal 1? Well, you get a1 1 plus a2 1 equal to 0. Okay, that's good. So we got an interesting relation from here. And finally, let's do x equal 2. You have a1 2 and then modulo. So 2 times 2 is 3 plus 1, which gives you a 1. So you get a2 1 equal to 0. Is that okay? So x squared at x equal 2 is what? It's 2 squared, which is modulo 1. It's 1 modulo 3. Okay. All right. Yeah, that's it. So we got these two relations, two equations, two unknowns, and you can just take their difference if you like. So you have a1 minus a1, and then these are 0. So you're forced with a1 0. So then you also get a2 0. That's it. All right, that's it. So for this polynomial set, we showed that the coefficients are forced to be 0. So indeed, this is linearly independent. Oh, okay, good. Lindsay asks a question. Why does x equal 1 yield 0? Why does x equal 1 yield 0? Good question. Okay, so let's clarify what's going on, right? So this statement here is required to be true for all x. Okay, so when someone asks for linear dependence, like let me do like a silly example from last time. What did we have? We had cosine 2x. We wrote it as cosine square x minus sine square 2x. Now this relation here is true for all x, right? So then we can say that we have dependence. So cosine 2x, cosine square 2x, and sine square 2x is linearly dependent. But only if you have it for all x. So it's the same idea here. We require this dependence to be true for all x in the modulo group. Is that okay? Oh, ignore me. Okay, I'm sorry. Wait, what's going on? So it'll be 2. Wait, never mind. Ignore me. So it'll be a2 times 4. No, that's what I'm saying, that it's a modulo group, right? So 4 is equal to 1 modulo 3. There is no 4. There's only 3 elements here, right? Okay, good. Great. All right. Good questions. Yeah, so another very famous example is you take all multiples of the exponential, and should we have some time? Let's see. Yeah, it's fine. We can talk about this stuff. Okay. All right. Okay, so yeah, these are independent, and let's check why. Right, so we ask for A1 EX, A2 E2X, and A3 E3X to be 0 for all X, let's say in the reals. Okay, so that's the requirement. That's a very strong requirement. Right, it has to be true for all numbers. So can someone give me two values of X where this, let me see, how shall I ask this? Maybe I should simplify it because it will be too hard for you. So let me do it for two of them. So it's a little bit easier. Yeah, let me do it like this. So at least for two of them, can you give me two values of X that will give us A1 equal to A2 equals 0? So one will be 0, right? What about the other one? Any guesses? So this one will give you, this is a very good choice. So it gives you A1 plus A2 is 0. Now we need one more. Any guesses? Yeah, let's try one. So what do you get? You get A1E and A2E squared. And anyways, the answer is it doesn't matter. You could have put any number here. But yeah, okay. So you get, you just need the 0, 1. Once you get the 0, 1, it's done. So you have A1 minus A2, and you plug that in the system. So you have A1E and then minus A1E squared. And then you just factor out E minus E squared. But this is not 0. So you get A1 is 0. So from here you get A2 is 0. So it didn't really matter. Yeah, any X, exactly. Yeah, any number of X will have worked. You just need to pick two different values. That's it. I just wanted to see, yeah, what do you guys think? Good. All right. All right. Yeah, so for cosine X, all this stuff, maybe we'll come back to it at the end if we have some time. But yeah, you can, it's a similar way. You pick different values like pi and 0. All right. Another beautiful example are what called nilpotent matrices. So this is a matrix that eventually becomes 0. Okay. I had an example somewhere. So this one, if you keep multiplying it by itself, you eventually get the 0 matrix. Okay. So it would be like this times itself. Eventually, if you do it r times, you get the 0 vector, the 0 matrix. I had an example somewhere. I should, I'll write it in the notes later. Okay, so this is the matrix. property, and then we take the set to be the multiples of A up to hitting the nilpotent power R. Okay, the claim is that this guy is linearly independent. So let's do that. All right. So as usual, you look at the relation A, identity matrix, A1, matrix A, and then AR minus 1, A to the R minus 1 equaling to 0. Okay, so this is the requirement, and we want to show that A0 to A1 to AR minus 1, they're all 0. Okay, so let's do that. Yeah, so the trick is you multiply by A each time. Okay, anyway, so let me do it. So you have A0A. So we multiply by A. And now here you see the last guy is 0. It's the 0 matrix. So this guy is out, 0 matrix. So you're left with A0A, A1 squared, all the way to AR minus 2, AR minus 1 equals 0. So hopefully you can see the pattern. You keep doing this, and eventually you end up with A0, A to the R minus 1 and a bunch of 0 matrices. So, okay. And just the first coefficient, A0. But we know, by assumption, AR minus 1 is not 0. So, yeah, it's not the 0 matrix. So that will give you that A0 is 0. So now you manage to get that the first coefficient is 0. Is that okay? And that's the trick. So now that you get the first coefficient to be 0, you play this game again. So you have now A1A, AR minus 1, AR minus 1 equaling 0. And you play this game again to get A1 to the R minus 1 plus 0 matrix to be 0. We know that it will be minus 2. We know that A to the R minus 2 is not 0. And so we get that A1 is 0. Okay, so you keep doing this for the kth coefficient, and indeed you will get A0 to A1 to A2, AR minus 1. They're all the 0 coefficients. Okay. Okay, if you have a question, let me know. Okay, yeah. So we got linear independence for this product, and you're free to use this result. Say I learned it in class, because it will show up later when we go into the spectral theorem stuff. I thought I should do a preview. Okay. All right. Oh, how do we make that rigorous? Like if we need to do it on assignment, we need to prove every step. Okay, okay. So let me do it all the way. So I did it for A1, and now you have to do it by induction. Okay, so now we have to do it for AK, for general AK, right? So this is the base case. Okay, and now we do the inductive step. So inductive hypothesis is that AK is 0. Show that AK plus 1 is also 0. Okay, so then we're left with AK plus 1, AK plus, what is it? Yeah, it's the same coefficient. All the way to AR minus 1, AR minus 1 equaling 0. And now you run down your argument again. So you do it once again, and you're left with AK plus 1, And then, yeah, so what is it? I have to multiply it by, well, we got, okay, so let me see, what do I want? So I multiply this guy enough times to kill all the other ones. So I have AK plus 2, and I multiply it by enough M so that this will equal AR. Okay, so K plus 2 plus M needs to equal R. So M is equal to R minus K minus 2. Okay, so I have K plus 1, and then I get plus R minus K minus 2. So this is AK plus 1. The K's cancel out. Yeah, I always get R minus 1. I don't know why. I'm sorry. I don't know what I'm thinking. Anyhow, so yeah, so we get that this guy is equal to 0. And but we know it's not 0. So we get that AK plus 1 is 0. So by induction, you got it for every single one. Okay. Well, R is fixed. You can fix R. R is the nilpotent power of the matrix. So R is fixed. From the set S is fixed. This is not the set of all matrices. You could, but then have the S. I'm not sure what you mean, but R is fixed. So we don't touch R. R could be like 100. So this is S of R, if you like. Okay, so we have a fixed matrix with a fixed R. Yeah, you work. Why AR minus? Oh, this is by assumption. We assume that. So the question is, why is not 0? This was our assumption that this R is the minimum. R is minimum, the minimum such that it's 0. Meaning for all the other ones, you have a non-zero matrix. Is that okay, Hu Yun? Okay. Will, is that okay for you? So R is fixed.
Yeah, I see now. Yeah.
Okay, good. Thank you. Yeah, all right. But that got me thinking, yeah, if you allow R to vary, you know what, let me see.
Yeah, couldn't you say like for any R, if R satisfies that relationship, then that set is linearly independent, and then do like
Right. So
induction on that?
I have to think of what the because when you talk about independence, you need like a concrete choice of vectors. Whereas in a way you have like a subspace, the way you describe it. Or maybe I'm wrong. Like, okay, I don't know. We can talk about this after, but I think your set will be like R1 to infinity. I'm sorry, guys. I'm just interested. We can talk about this after, yeah. And then maybe this guy is linearly independent. But yeah, that's pretty cool. I haven't thought about this. Yeah, there you have to do double induction. Okay, that's nice. All right. All right, so these are some results from the book. Let me prove them. So, okay, so suppose you have a set S, it's linearly dependent, and then take any larger set. So you have, let's say S is V1 to Vn, and take S prime to be V1 to Vn, and then you add some other stuff like W1 to Wm. Let me just add one more, it doesn't matter. Let me keep it simple. Okay, the claim is that this guy is also LD. And I think it's pretty easy to see, right? Because the condition of LD, the condition of LD is the following. It says that that if you that the relation A1 V1 AN VN equal to 0 holds for some AI in the field and VI in S. Okay, and at least one of them, and at least one AI, let's say AJ, is not 0. But it's for some of them. You don't have to do it for all of them. So I know I wrote it like this, but even if you just had A1 V1 plus A2 V2 equaling 0, for A2, let's say not 0, then you still have linear dependence. Okay, so you still have linear dependence, even though you only look at a subset of the vectors. So this is just parsing definitions together. So here, so just take the first n of them, which you already know. So you write it like this, and then put 0 times W1 equaling 0. Okay, this guy is irrelevant because it's just a 0 element. And we know that this is true. It's true that it's equaling 0 for some AJ not 0. So indeed, we have the relation. Okay. Is that okay? Oops. So yeah, if you have a question, let me know. So if you see something like this, what do? You know this implies this. So call this star. I will start writing proofs more formally since people want to, yeah. And then you look at this relation, and then you use star over here. You know this to be true for some AJ not 0. So indeed, S prime is LD as well. Okay. All right. Let's do another one. Right. So now you have the other situation. You know that SV1 to Vn is Li. Show that if you're inside S prime, like, I don't know, Vn to Vm for m less than n is also Li. Okay, so let's do this carefully. So here you have that if you have this, then you get all of them to be 0. So let's do it here. B1 V1 all the way to Bn Vm equaling 0. Okay, we want to get that the BIs are also 0. Let's see. So how do we do this? Well, we know that this is equal to B1 V1 Bm Vm, and then you add the rest of them. So 0 Vm plus 1 all the way to 0 Vn. And here you use S is Li. Okay, so you get that B1 is equal to B2 all the way to Bm. And these are equal to the 0 coefficients. So this is Bm plus 1 and then Bn. Okay, that's it. Oh, there's some questions. So presumably any subset of an Li set will be Li, yes, and any superset of LD will be LD, yes, but there's ambiguity in the case of a subset of an LD set because set that is LD. Yeah, okay, so let me go over that. Can we just simply say that it has the same element as S, and that's by default it has to be LD? No, I will do an example for Kellyan, And yeah, let me start with the Lindsay example. So, okay, sorry, what did Lindsay say? Take a set S that is LD, could have a subset that only takes element of S. Right. So I think we did this, right? So take a 1, 0, take 1, 1, and then take 1, 2. This guy is LD, but a subset of it, the 1, 0, 1, 1, is Li. So yeah, it doesn't always carry through. This guy is Li, and then another subset, take the yeah, maybe I should add more vectors. Let me add one more, maybe something like 2, 2. So this guy is Li, and then you could also take another subset, the 1, 1, 2, 2. This guy is LD. So you could have both things happen. You can have a subset that is Li and also a subset that is LD. Is that okay? And then, I mean, for a subset is LD, that's a superset, has to be LD. Yeah, this is the result we just proved, Kellyanne. So if you have a subset that is linearly dependent, then the big set will also be linearly dependent. Can we just simply say it has the same elements as this? It does. Oh, by same, I thought you meant same size. I'm sorry. Yeah, absolutely. Yes. Our empty sets. Yeah, so Kellyanne, exactly. Yeah. But that's what I'm proving. So we have to prove it, write it down like in symbols. But yeah, you're right. There's not much content there. Okay. Are empty sets Li or LD? Are empty sets, yeah, so this is in the book, right? So the empty set is by definition, so let me write the zero vector. The zero vector, in a sense, okay, I mean, how should I say it? Yeah, anyhow, so empty set is taken to be dependent. I mean, it doesn't even make sense to, because you can't even write down the, so the reason, it's sort of trivially true, right? Because take this to be V, then you have AV is 0, but then this is like vacuously true, true for all A, not necessarily 0. So I don't know. I wouldn't worry about it too much. We wouldn't put something like this. It will confuse people. Okay. All right. This was an exercise, so I have some time. I wanted to do this theorem, that maybe I have to do it now. Yeah, let me prove a result that I definitely need for Friday. And then if we have time, we come back. These were exercises in your book. I wanted to do them because they're pretty cool. So if we have time, we'll come back to it, but I have to prove this result for Friday. All right. Okay. So here's the thing. We have linearly independent sets, and we have the concept of span, right? So for example, you have this guy 1, 0, 1, 1, and 1, 2. Now this guy has span equal to R2, right? It's the whole space. But the same is true for S prime, where you just kept the first two. You also have span of S prime to be R2, right? So you have this and you have this. And the claim is that, yes, the claim here is that S prime can have size at most S. So if you know that S is a spanning set and it has some size here, S is 3. And if you give me any linearly independent set, then its size will at most be the size of the bigger set. Okay. That's because you can always, that's because you can always add redundant vectors. You can always add redundant vectors to an Li set. Okay, that's sort of the what's going on here. So let's talk about this carefully over with the proof. And any questions? Oh, and a span that is linearly independent is a basis, right? That's right. Yeah. So we will talk about this on Friday. So that's yeah, that's the motivation for this stuff. Okay, so let's prove this result. So again, we have a set S and we know that it spans the whole thing, but it could have redundant vectors in it, like we said, 1, 0, 1, 1, and 1, 2. This guy over here or the other one is redundant. So yeah, anyhow, so it's redundant. And then we also look at another subset T, W1 to WK. And by contradiction, we assume that the LD set is bigger than the size of the spanning set. Okay, so span of S is the whole thing. And we assume that in fact, T has even more elements than the spanning set. Okay. We will do it by contradiction because we want the reverse. Okay. All right. So here's a nice claim. So like we said, this is the whole space V. So, and T is inside V. So we start with the first element, W1. We know that this is in the span of these guys, V1 to Vn. So here's the claim. This was, I think, an exercise, but I want to do it. So it says that you can find the Vj element, that you can replace it by W1. Okay, this is a very general thing. This is, it doesn't have to do with our specific result. So let me prove you that. Okay. All right, let's prove this result, that you can always replace at least one of the elements by another element that you like. So I guess an example would be, you know, you have the 1, 0, 1, 1, and 1, 2. This is your S, and then take W1 to be, I don't know, 1, 3. Okay, in this case, you can get an S prime to be the 1, 0, 1, 1, and then you can replace the third guy. That's the idea. Okay, so we do like a replacement trick. All right, so how do you do this? Since W1 is in the span, you can write it as a linear combination over here. Okay, so we do that. And then since it's a linear combination, it means that there exists at least one non-zero AJ. If they were all 0, then it's not a linear combination. You need at least one of the coefficients to be non-zero to talk about linear combination, right? You can't, like, yeah, like 1, 3, if you say 0, 1, 0, and 0, 1, 3, first of all, this is false, or 1, 2. So you need at least one of them to be non-zero. Okay, so since it's not 0, you have a multiplicative inverse. All right. So since you have a multiplicative inverse, you multiply both sides by it. So we do it here. Okay. And I'll just finish with the claim and continue on Friday. So now if you give me any X in the span, what do? You have your linear combination and then you replace Vj. Okay, so I replace the Vj by the W. Okay, so that was the trick. So that just changes the coefficient. So I get C1V1 all the way to CJW, all the way to CNVN. And this is an element of the span of V1, W, Vn. Okay, so we'll continue our proof on Friday as a prelude basis. Okay, thank you.
Hello, Professor. I had
Yeah.
a question.
Yeah.
I'm like, essentially, like from the reading quizzes, like there was one question on like if there were several options on R plus, right? So like one of the options which like I thought is right, which was marked false, was that R plus is not a subspace. Like R plus is a subspace of R. So
So R plus, meaning
Uh-huh.
all real numbers that are bigger or equal than 0, you mean?
Or strictly more than 0. Yeah.
Okay, sure.
Uh-huh. And the addition is defined as the multiplication of the numbers, and the scalar multiplication is defined as exponential. Uh-huh.
So multiplication is
X
addition
dot
is
y.
defined as multiplication.
Uh-huh. And the scalar multiplication is defined as x to the power of a. Yeah.
I see. Okay,
So
that's good.
so with these operations, is R plus a subspace?
So
of
what was
R?
the answer? I mean, I can check, but I don't know.
Yeah, but I think as well it is a subspace, but like
So
it
wait,
was
is that
marked.
the current reading quiz or what?
It was the second one, I think. Reading
Okay,
quiz
so
2.
there was no answer to the quiz?
Oh, like like I selected it, but it was marked as false. That's why.
Okay, so wait a second. So you selected this to be a subspace.
Yes, I selected this as a subspace. Like
So
there were
it's not a
multiple correct.
subspace.
I think it's a subspace, and it might be mistaken at the question that it's not a subspace. That's why I
No, I
wanted to
don't
ask
think.
you.
I think Camille is pretty careful. So
Mhm,
let's see. So one of the axioms fails. I'm not sure which one.
mhm.
So probably
It's true that it is a vector space. It was proven, since there were multiple correct. It was proven that it is what do you say? It is a vector space for sure.
just a second. So subspace of which space?
Of R, yeah. Mhm.
Like with the same operations?
Yes, yeah.
No, but I mean, that doesn't even make sense because you cannot take -1 to the, I don't know, a half or like 1/4.
Oh, but like since it's -1 is not an R plus, right?
I don't understand. When you define subspace, you have to be careful, right?
Uh-huh.
You need to define operations for the bigger space. So what will be the bigger space?
Okay. Like, oh wait. Is it okay if I like share my screen and show you the question?
Sure, yeah. I mean, I'll just go find the question.
Yeah.
You know,
Mhm.
let me see. Okay, just a second before we go into your thing. I think, does anybody have questions about what we did today? Like,
Sure,
is there
sure.
any?
Yeah.
Just a second. So, because I should have not gone. Do people have questions for what we did today? I should do this first. I mean, I don't see anything. Okay, let me find this timeline. Yeah, okay, same thing. I see. Okay, where is this? So reading quiz, and then what was the number?
I think it was wait, it was question 1. Yeah, yeah, first one.
What?
The first one, reading quiz 2. Yeah. The R plus example from 1.1.4.
Right, in this question, plus and minus refer to addition. Reread the definition, choose all the correct statements.
So even though it's I'm not sure whether the ordering of options are same, but one of the options is that R plus together with plus apostrophe and dot apostrophe is a subspace of R, right? So that one,
Yeah,
like I
so
selected
I
that.
mean,
Uh-huh.
I don't know what to tell you. Like,
So, like, is that true or false initially? Maybe I'm mistaken. Yeah.
well, I mean, well,
We know it's
I
a
mean,
vector space
okay,
for
just
sure.
a second. Do you
Uh-huh.
understand that R plus
Mhm.
is only a vector space because of this new operations,
That's
right?
right. Yeah.
So if
Uh-huh.
you have other operations, like if you allow like, -1 times X, then you
Uh-huh.
don't have closure.
That's right. Uh-huh.
Yeah. So I don't know, which part are you talking about?
Wait, can I share my screen because my one
No,
is
just I'm
glazing?
looking at the quiz right now. Can you tell me can you repeat which one you chose and you said wrong?
Sure. So like I chose 3 of them. First one, which is correct, R plus together with plus
Yeah, but which
apostrophe.
one got wrong? Just tell me.
R plus together with plus apostrophe and dot apostrophe is a subspace of R.
Yeah. So, okay, that makes no sense, right? Because R
Mhm.
is not a vector space with those operations.
Oh, wait, but like there was another option.
Okay, let
which
me
is correct.
clarify. When we talk about subspace of something,
Mhm.
we are preserving the operations of the larger space. You don't get to change the operation.
Okay.
Okay, good.
So even though like in the option they were like with the operations this and this, that doesn't matter because the operations that we'll be considering will always be of the superset.
Yeah. So this is a tricky choice or tricky option, just to see that whether you understand that the operations have to match those of the larger space.
So because the operations don't match, it's false, and that makes much more sense. Yeah.
Yeah.
Thank you so much. Yeah.
Yeah. Kellyanne, is that okay for you? I was wondering. Yeah, it has to have the same exactly as the superspace. Exactly. Yeah, you can just talk, Arshia.
Hi, Professor. I had a question about the written assignments. Can I ask you?
Like what?
Not like just a clarification in the questions, like
Sure,
not
yeah.
to check my answer. It's actually about the first problem, number 3. I can't really share my screen. I don't know if you have access to the. Do you have access to the written assignment? Like, do you see the questions? Maybe I can try.
No, just a
share.
second. Let me find it.
Oh,
So
okay,
you're
okay.
talking about homework 1, right?
Yes. There's only homework 1. Question 1, part 3.
That's why we have office hours. This is not really the place for.
Sorry.
But okay, no,
I can
never
ask
mind.
an
Okay,
office
just
hour.
a second. So yeah, part 3. Yes, I'm looking at it. Yep. Okay.
Yeah, so it says so we extend addition to all elements of, it says R union infinity minus infinity cross R union infinity minus infinity, right?
Right.
So but the thing in question 3 is still only the set R union like it's not a cross, it's like just one dimension, right? R union infinity minus infinity. That's the thing we're supposed to check if it's a vector space or not.
I don't understand. So when we talk about addition is a function, right? And it has 2 inputs.
Oh, so that's why we do a cross.
Yeah,
but the actual set in question, like the thing I'm supposed to see if it's a vector space.
That's right.
Oh, okay. Okay, that was my question. Okay, thank you very much. All right, that's it.
That is a tricky one. The tricoloring, hopefully you guys will get it. I don't even know if they're gonna mark what they're gonna mark. Yeah. Any questions? Can be about anything, it's fine.
Oh, if possible, we'll
Yeah,
get,
yeah.
It's okay. Sorry. So in the same written assignment, problem 2, number 5.
Uh-huh.
Number 5 says, give an example of the vector spaces, and then it says explicitly verify the implication in like the implication of the statement in part 4.
Yeah.
But part 4 is an if and only if, so it's 2 implications. So am I supposed to verify? Like, what am I supposed to verify, really?
Well, I mean, what do you think? Like, suppose
Like-
you find this example, right? And you have containment, right?
So yeah, I'm supposed to show that.
No, well, like,
basically,
because I keep seeing this question on Piazza. I'm not sure people like, so you have U is in W or W is in U. That's your example. Like you build an example.
yeah, so that's what came to my mind, and then based on that, I show that U union W is also a subspace, which
right.
is
But then
go ahead.
just a second. So then, suppose you wanted to do the converse. It wouldn't make any sense because you already know that you have
Exactly. Yeah,
containment.
that's the problem I ran into. But
Well, it's not a problem. It's just you only need to do one direction because your example already has
The
one
fact
of
that
the
it's a-
directions. Yeah.
Oh, okay.
Yeah.
That's just, I guess, my bad on not the understanding. Okay, and just one more question. It's for the knot diagrams. When we talk about one diagram, we mean every single, like the whole knot, right? Like we don't mean just one crossing. So like if it says a tricoloring is like an entire knot diagram with every segment like colored, in the appropriate colors, right? Not just like one intersection. Am I understanding that correctly?
I mean, yeah, it's like the trefoil has 3 segments. So if you carefully look at it, yeah, it's composed of 3 parts.
So
So that's
each one tricoloring is each of those parts has a color, right? Like the whole diagram.
yeah. So
has-
you have 3 segments and you can put 3 colors on it. And there's some
Oh, okay.
rules on, so every segment corresponds to it's like a component.
Yeah. Okay. All right. I'll bring up any other questions in office hours. I don't want to keep you. Thank you so
Or on
much for this.
Piazza, it's fine. No, you can say, I mean.
Well, nothing for now. It's just, because
Okay,
I have to think about it myself. Yeah. Thank you so much, sir.
Yeah. All right. I don't see any other question. See you guys.